The first human who steps onto the surface of Venus will be dead before their second foot leaves the ladder. Tonight, we're going to walk through the most hostile solid planetary surface any human could realistically try to reach. In this video, we will look at exactly what kills you, second by second, the moment your suit fails on the surface of Venus. We will examine the 467-degree heat. We will examine the 92 atmospheres of pressure crushing your chest from every direction. We will examine the first impossible breath, superheated carbon dioxide, no oxygen, and air dense enough to behave less like the air on Earth and more like a hostile fluid. We will examine why Venus, the brightest object in our night sky, the planet most similar in size to Earth, became the deadliest place in our solar system. And we will sit with the strange fact that 10 Soviet probes have already landed there, the longest one surviving for 2 hours and 7 minutes before the planet finally killed it. By the end of tonight, you will understand why no human being will ever survive the first second on Venus. Before we begin, get yourself comfortable. Pull a blanket over you. Settle deep into your chair or your bed, and let the room around you go quiet. We are not going anywhere tonight. We're going to take our time. If you enjoy the kind of careful, slow, science-honest walks we take here, a quick like or subscribe really helps the channel reach more people. Small for you, real for me. We begin. If you have ever stood outside on a clear evening, just after sunset, and seen a single brilliant point of light hanging low in the western sky, brighter than any star, brighter than anything else above you, then you have already met Venus. Venus is the brightest planet in our sky. After the sun and the moon, it is the third brightest object visible from Earth. On the right night, it can cast shadows. People have mistaken it for an aircraft. People have called the police about it, thinking they were seeing something unusual or unidentified. They were not. They were seeing our nearest planetary neighbor, doing what it does on most clear evenings, hanging in the sky and reflecting an enormous amount of sunlight back toward us. That brightness is the first thing to understand about Venus, because it is the first thing the planet tells us about itself, and almost everything it tells us is a lie. Venus is bright because its atmosphere reflects somewhere between 75 and 80% of the sunlight that hits it. Almost nothing else in the solar system has an albedo that high. Earth reflects about 30%, the Moon around 12%, Mars 25%, Venus 3/4. The planet is wrapped in a permanent shroud of pale yellow-white clouds that bounce sunlight back into space the moment it arrives, which is why we see Venus as a brilliant clean point of light from 100 million kilometers away. That same shroud is what makes the surface of Venus the deadliest planetary surface in our solar system. Tonight, before we get to the body, before we get to the second-by-second story of what would happen to a person who stepped onto the surface, I want to be honest with you about what the title of this video means. The title says no one will survive a single second on Venus. The title is not exaggerating, but the title also does not mean the body disappears in 1 second. It means the fatal process begins instantly. The pressure, the heat, the carbon dioxide, and the lack of oxygen all hit at the same moment. There is no safe first breath. There is no adjustment period. There is no rescue window. The surface of Venus does not give a human being a chance to react, to call for help, to retreat back into the airlock. Everything that ends a human life is already happening before the second foot ever lifts off the ladder. That is what the title means. The killing begins instantly, whether the body lasts 1 second or 3 or 10 before consciousness ends. The outcome is settled in the moment of contact. Now, with that honesty in place, let us look at the planet itself. Because the strangest thing about Venus is not that it is hostile. Many places in our solar system are hostile. The strangest thing about Venus is that, by the simplest measures we have, it should be one of the most familiar worlds we know. It is the wrong size for what it is. It is the wrong gravity for what it is. It is the wrong place for what it is. Venus is roughly the same size as Earth. It is 95% of Earth's diameter. It is 81% of Earth's mass. Its surface gravity is 90% of what you feel right now, sitting wherever you are sitting. If you stood on a planet that was identical to Venus in mass, size, and gravity, but had Earth's atmosphere instead of its own, you would feel almost no difference from home. The ground would press up under your feet, with familiar force. The air would taste right. You would walk and move and breathe the same way you walk and move and breathe at home. Venus is the closest thing to Earth that exists in our entire solar system, by the basic measures of what makes a planet what it is. And it would kill you in seconds. That is the first contradiction of Venus. And it is the contradiction the rest of this video is built around. The world most similar to ours, in our own neighborhood, is the place that would kill us fastest. It is not what it pretends to be. There's a phrase that planetary scientists sometimes use when they are talking about Venus. They call it Earth's evil twin. The phrase is informal. You will not find it in a textbook, but it captures something true about how strange Venus actually is. When you compare it to our home, point by point, same size, almost exactly. Earth is about 12,700 kilometers across. Venus is about 12,100. The difference is about 5%. Same mass, almost exactly. Earth weighs in at 6 times 10 to the 24th kilograms. Venus weighs in at 4.8, 7 times the same scale. That is about 81% of Earth's mass. Same gravity, almost exactly. The surface of Venus pulls on you with about 90% of the force you feel on Earth. A person who weighs 100 kilograms here would weigh about 90 kilograms there. Same density, almost exactly. Earth's average density is 5.5 grams per cubic centimeter. Venus's is 5.2. The interiors of the two planets are made of similar things, in similar proportions. Both have iron cores. Both have rocky mantles. Both have thin crusts on top. Same neighborhood. Venus is the second planet from the Sun. Earth is the third. They both formed from the same protoplanetary disk 4.5 billion years ago, out of the same rough mix of dust and rock and ice and gas. They are siblings, in the most literal sense. They came from the same place at the same time. By every measure of what a planet is made of, and how a planet is built, Venus and Earth should be twins. And then you look at the surface. Same body, different fate. Earth's surface is, on average, 15 degrees Celsius. Venus's surface is 467 degrees Celsius. Earth's atmospheric pressure at sea level is 1 bar. Venus's surface pressure is 92 bars. Earth's atmosphere is mostly nitrogen and oxygen. Venus's atmosphere is 96% carbon dioxide. Earth has rain. Venus has clouds of concentrated sulfuric acid that never reach the ground. Earth has plate tectonics, oceans life. Venus has volcanic plains, no oceans, no liquid water of any kind, and no living thing that we have ever found. The two planets started in the same place. They became different worlds. How that happened is one of the deeper questions in planetary science. We will return to it near the end of tonight, after we have walked through what Venus is now. The path that took Venus from sister planet to the world we have been describing involved its closer distance to the Sun, the slow brightening of the Sun over billions of years, and a runaway feedback in the atmosphere that, once started, did not reverse. None of those individual factors, on their own, would have transformed an Earth-like world into what Venus became. The combination did. This is one of the deepest mysteries in planetary science, and it is the question we're going to come back to near the end of tonight. How can two worlds, born together, with the same basic ingredients, end up so completely different? Why did one of them become a place where life arose and continues, while the other became the place that would kill us fastest? The answer, as best we currently understand it, has to do with the Sun, with timing, and with a feedback process that only ran in one direction. We will get to all of that later. For now, what matters is that the comparison is real. Venus is not a strange alien world that we cannot recognize. Venus is something much stranger than that. Venus is what Earth might have become, under slightly different conditions, billions of years ago. That is what makes the planet uniquely terrible to study. It is close enough to Earth to feel familiar. It is hostile enough to kill any unprotected human in the first second of contact. And the gap between those two facts, the familiar size and the lethal surface, is the gap we're going to walk through for the next 2 hours. Same body, different fate. Hold that idea, because the rest of the video pushes on it from every angle. To talk honestly about what happens to a person on the surface of Venus, we have to start with the numbers. 3 numbers, specifically, that define everything else about the surface, and that are the reason no human can survive there. The first number is 467 degrees Celsius. That is the average surface temperature. 872 degrees Fahrenheit, if you prefer that scale. To make this concrete, a few comparisons. Lead melts at about 328 degrees Celsius. Tin melts at 232. Zinc melts at 420. The surface of Venus is hot enough to melt all three. A pure ingot of lead, placed on the basalt of Venus, would slump into a puddle within minutes. A pure ingot of tin would do the same in seconds. Most cooking ovens, set to their highest temperature for things like cleaning cycles, reach somewhere around 470 degrees Celsius. The surface of Venus is the inside of a self-cleaning oven, running permanently, on every square meter, day and night, pole to equator, with no break and no relief. That is the first number, 467. The second number is 92. That is the surface pressure, measured in units of Earth's sea level atmospheric pressure. 92 bar. 92 times what you feel right now, in every direction, against every centimeter of your body. To make this concrete, the equivalent on Earth is being submerged about 900 meters underwater, almost a kilometer down, deeper than any human has ever free-dived, deeper than the working depth of a nuclear submarine, a pressure that would collapse the ribcage of an unprotected diver almost instantly, that would crush most ordinary engineering structures, that would compress the air in your lungs into a fraction of its volume. Standing on Venus is not standing in air. It is standing under a fluid almost as dense as the deepest ocean trenches on Earth. Two numbers down, 92 and 467. The third number is 96. That is the percentage of Venus's atmosphere that is made of carbon dioxide. 96%. The remaining 4% is mostly nitrogen, with traces of sulfur dioxide, water vapor, and a few other compounds. There is essentially no oxygen at all. Less than a few parts per million. Not enough to support a single breath of any animal that has ever lived. A human being standing on Venus, with no breathing apparatus, would not be able to inhale anything that resembled breathable air. The first attempted breath would draw in superheated carbon dioxide at 467 degrees, at 92 bar of pressure. That breath would not feed the body. It would damage it. This is what the title of the video means, in concrete terms. 3 numbers. Each one alone would be lethal in seconds. Together, they leave no possibility of survival, even for an instant longer than the suit's failure. The air does the killing. It is worth pausing on that, because it is the central truth of Venus, and it is the truth most people miss when they think about planetary danger. We're used to thinking about hostile environments as places with too little of something. Vacuum, cold, radiation. Mars is hostile because it has almost no atmosphere. The moon is hostile for the same reason. The vacuum of deep space is hostile because there is nothing there at all. Venus is the opposite kind of hostile. Venus is hostile because there is too much pressure, too much heat, too much carbon dioxide. The atmosphere is not a thin shell to be escaped. The atmosphere is the weapon. A human being is a system designed for 1 bar of pressure, 20% oxygen, 15 degrees Celsius, in an atmosphere that is mostly nitrogen and oxygen with a little water vapor. Every part of human biology assumes those conditions. The lungs, the cardiovascular system, the skin, the eyes, the nervous system, all of them are tuned to the air of Earth. Venus does not have that air anywhere. Not on the surface, not in the lower atmosphere, not for the first 40 kilometers up. Venus has its own air, and that air is one of the most efficient killing systems anywhere in the solar system. The most Earth-like planet in our solar system is the most hostile place a human will ever encounter, and the reason for that is mostly in the air. To understand why Venus is so hot, you have to deal with a fact that surprises most people the first time they hear it. Venus is hotter than Mercury. Mercury is the planet closest to the Sun. It is the first planet, the one that orbits inside Venus's orbit, the one that gets the most direct sunlight of any planet in the solar system. By every intuition, Mercury should be the hottest place. The closer you stand to a fire, the hotter you feel. Mercury is the closest body to our solar system's fire. And yet Venus, the second planet, is hotter than Mercury at every point on its surface, by every measure. Mercury's daytime surface gets up to about 430 degrees Celsius. Venus's surface, average, all the time, is 467. Mercury's nighttime surface drops down to negative 170 degrees because Mercury has no real atmosphere to hold the heat. Venus's nighttime surface stays at 467 degrees. Same temperature, day or night, summer or winter, equator or pole. That uniformity is the clue. Venus is the same temperature everywhere because Venus has an atmosphere that does not let heat escape. Mercury is wildly different day and night because Mercury has almost no atmosphere at all. The presence or absence of an atmosphere is what determines whether a planet's surface temperature stays stable, and what determines how high that stable temperature climbs. What happens on Venus is what climate scientists call a runaway greenhouse effect. The phrase has become familiar in the context of climate change on Earth, but the version on Venus is the most extreme example of the process anywhere in our solar system. Understanding it carefully is worth the time. Here is how it works. Sunlight arrives at Venus's outer atmosphere. Most of it, about 3/4, is reflected back to space immediately by the cloud tops. That is what makes Venus so bright in our sky. But the remaining quarter does penetrate the clouds. It works its way down through the atmosphere, growing fainter as it goes, but reaching the surface in the end as a dim, warm glow. The sunlight that reaches the Venusian surface is roughly the equivalent of a heavily overcast day on Earth. The sunlight warms the surface. The surface, in turn, radiates that heat back upward in the form of infrared light. This is what every planet does. Sunlight in, heat out. The planet stays in thermal balance as long as the heat going out matches the heat coming in. But Venus's atmosphere is mostly carbon dioxide, and carbon dioxide is, at the molecular level, very good at absorbing infrared light. Heat radiating up from the surface tries to escape into space. It hits the carbon dioxide. The carbon dioxide absorbs it. Then it re-emits the heat in random directions, and a lot of that re-emitted heat goes back down toward the surface. The heat cannot leave. It just bounces around inside the atmosphere, between the carbon dioxide molecules, until it eventually finds a way out at the very top, where the atmosphere is thin enough for infrared light to escape into space. But it takes a long time to get there. And while the heat is taking that long time, more sunlight is arriving from the sun, and more heat is being added. Over billions of years, this process built up. The atmosphere of Venus accumulated more and more heat, until it reached the present steady state. The surface temperature is what it is, because that is the temperature at which the heat going out finally balances the heat coming in. Lower than that, more heat would build up. Higher than that, more heat would escape. The system has settled at 467 degrees, and it does not move. The heat has nowhere to go. That is the key sentence about Venus. The heat has nowhere to go. The atmosphere has trapped it, and the atmosphere will keep trapping it as long as the atmosphere stays the way it is, until the sun goes out, or until something dramatic happens to the atmosphere. The surface temperature will remain what it is. It does not vary by season. It does not vary between day and night. It does not vary by latitude. The whole planet, all of it, sits in the oven, all the time. There is something almost calm about that uniformity. On Earth, the surface temperature swings dramatically. Sahara summers reach 50 degrees Celsius. Antarctic winters drop below -80. Every part of Earth's surface experiences daily and seasonal changes, sometimes by tens of degrees. The Earth is alive in that variation, in a sense. Weather happens. Wind blows. Currents flow. The planet's surface is in constant thermal motion. Venus has none of that. The surface is the same temperature, everywhere, all the time. There is no weather in any meaningful Earth-like sense. There is no daily warming. There is no seasonal cycle. The planet's surface is, by the measure of temperature variation, the most monotonous large surface in the solar system. Hot, static, still. Mercury, by contrast, has no real atmosphere to do this trapping. The sun heats Mercury's daytime surface. The heat radiates back into space immediately. There is no greenhouse blanket. The temperature drops fast as soon as the surface is in shadow. Mercury is hotter than Venus during the day in some places, very briefly, but the average temperature, across the whole surface, across all times of day, is much lower on Mercury than on Venus. Because Mercury cannot hold its heat, Venus cannot let go of its heat. That is why being closer to the fire does not mean being hotter. Venus's atmosphere has built itself a heat trap that overwhelms its slightly greater distance from the sun. The atmosphere wins. The atmosphere always wins on Venus. It is the most powerful single feature of the planet, and it is the feature that will kill any human who tries to walk on the surface. We have looked at the heat. We have looked at the pressure. We have looked at the air. Now we have to look at the strangest part of all, the clouds. Above Venus, draped permanently around the entire planet, in 3 thick layers between 48 and 68 kilometers above the surface, are the most chemically aggressive clouds in the solar system. The clouds of Venus are not made of water. They are not made of methane, like the clouds of Titan. They are not made of ammonia, like the upper clouds of Jupiter. The clouds of Venus are made of concentrated sulfuric acid. By weight, depending on which layer you measure, the cloud droplets are between 75 and 96% sulfuric acid. The rest is water and trace compounds. To put that in context, the sulfuric acid you might find in a car battery is about 33% concentration. Industrial-grade sulfuric acid for laboratory use runs around 96. The clouds of Venus, in their lower layers, are essentially industrial-grade sulfuric acid, suspended in droplet form, drifting permanently across the entire planet. These clouds form through a chemical chain that runs entirely on Venus's own resources. Sulfur dioxide, released by ancient volcanism, drifts up through the atmosphere. Water vapor, in tiny amounts, also drifts up. Ultraviolet light from the sun strikes the upper atmosphere and breaks apart molecules. The fragments recombine. Sulfur dioxide plus water plus ultraviolet light produces sulfuric acid. The acid condenses into droplets, and the droplets become clouds. The clouds drift westward across the planet, propelled by powerful upper atmosphere winds that move at up to 360 kilometers per hour. The cloud layer circles the entire planet about once every 4 Earth days. The whole planet, in other words, is wrapped in a fast-moving acid weather system that never stops, never breaks up, never has a clear day. Now, here's the part that matters for the surface, and it is the part most people get wrong. The acid is mostly above you. The surface does not need acid rain to kill you. The air itself is enough. I want to spend a moment on this, because it is one of the most common misunderstandings about Venus. People hear sulfuric acid clouds, and they imagine acid rain falling on the surface, eating through whatever is down there. That is not what happens. What happens is this. The sulfuric acid droplets, in the cloud layer between 48 and 68 kilometers up, do sometimes fall as a kind of acid rain. But the surface of Venus is so much hotter than the cloud layer that any falling droplet evaporates long before it reaches the ground. The droplets fall. The air below the clouds is too hot for liquid acid to exist. The droplets vaporize back into gas. The gas drifts back up into the cloud layer, where it cools enough to condense again into droplets. This cycle, called virga, means there's acid weather happening above the surface, but no actual acid rain ever lands on the rocks below. The surface of Venus is dry. There's no acid pooled on the basalt. There is no acid puddling in cracks. The surface is hot, dry, dimly lit basaltic plain, with corrosive carbon dioxide above it, but no liquid acid. So why mention the acid clouds at all, if they do not reach the surface? 2 reasons. First, because they are part of why Venus is what it is. The acid clouds are part of the atmospheric system that traps heat, that maintains the runaway greenhouse, that contributes to the planet's pale yellow appearance from space. Without the acid clouds, Venus would not have the atmosphere it has. Second, because the acid layer matters enormously for any future mission to Venus. Any spacecraft, any balloon, any aerostat, any flying probe that operates in the upper atmosphere of Venus will have to survive direct contact with concentrated sulfuric acid. The acid does not eat the surface. It would absolutely eat a poorly designed spacecraft. But for the question we started this video with, the question of what kills a human being on the surface, the acid is not the killer. The killer is the air at the surface itself, the carbon dioxide, the pressure, the heat. The acid is the storm above your head. The killer is the weather you are standing in. It is raining poison that never lands. That is the strangest thing about the surface of Venus. The most chemically aggressive clouds in the solar system are above you, all the time, but they are not what you have to fear. What you have to fear is the air itself. What you have to fear is the pressure compressing every part of your body. What you have to fear is the temperature heating every surface around you. The acid is real. The acid is overhead. But the acid is not the executioner. The air is the executioner. Now, with the heat, the pressure, the carbon dioxide, and the acid all in place, we can finally turn to the part of the story that matters most. Because before any human ever tries to stand on the surface of Venus, machines already tried. 10 of them landed and lived briefly. The story of those 10 machines is the closest thing we have to a real account of what Venus does to anything that touches it. We turn now to the Venera probes. Before any human ever tries to stand on Venus, machines already tried, and Venus killed every one. Between 1961 and 1985, the Soviet Union ran one of the most ambitious planetary exploration programs in the history of spaceflight. They called it Venera, the Russian word for Venus. Over 24 years, they launched probe after probe at the planet, learning from each failure, hardening each design, sending more sophisticated machines into the atmosphere again and again. 10 of those probes successfully landed on the surface of Venus and returned data. None of them survived for more than 2 hours and 7 minutes. Every one of them died there. The story of the Venera program is the story of the only human-built objects ever to touch the surface of Venus and live long enough to tell us what it was like. Each probe was a kind of forensic instrument. Each one survived a slightly different time, in a slightly different way, and gave us slightly different information about what the surface actually does to whatever lands there. We're going to walk through the most important of these missions, in order, because the story they tell, when you put them together, is the closest thing humanity has ever come to a first-hand account of standing on Venus. And the answer they all gave us, regardless of design, regardless of armor, regardless of cooling, was always the same. Venus wins. The early Venera missions, from 1961 through 1969, were a series of mostly failed attempts. Venera 1 launched in 1961 and lost contact a week after launch. Venera 2 lost contact after leaving Earth orbit in 1965. Venera 3 became the first human-built object to touch the surface of Venus in March 1966, but it was a hard impact. The spacecraft did not survive the descent, and no data was returned from the surface itself. Venera 4, launched in 1967, became the first probe to transmit data from inside the atmosphere of another planet. It descended through the upper layers, returning measurements of pressure and temperature, until at some point during the descent the spacecraft was crushed by the pressure and the transmission stopped. Venera 4 did not reach the ground. The crushing came first. The same fate met Venera 5 and Venera 6 in 1969. Both descended through the atmosphere. Both transmitted data for a while. Both were destroyed by the pressure before they could land. Each one penetrated a little deeper than its predecessor, but none of them survived contact with the surface itself. By the end of the 1960s, the Soviet engineers had a very specific problem on their hands. The atmosphere of Venus was thicker, hotter, and more crushing than they had originally believed. Every probe they had sent had been destroyed before it could touch the ground. To land successfully, they needed a spacecraft that was less like a satellite and more like a deep-sea submarine, a bathysphere, a vessel built to withstand pressure of a kind that had never been engineered for spaceflight before. It is worth pausing on the human side of this for a moment. By the late 1960s, the Soviet planetary program had spent nearly a decade and an enormous amount of money trying to land on Venus, and they had nothing to show for it. Every probe they sent had been destroyed before it could complete its mission. The American program, which had been pursuing both Venus and Mars, had taken some early Venus measurements through flybys, but had largely shifted focus to Mars by this point. The Soviets had committed themselves to Venus, and Venus had, every time, killed their machines. The engineering team responsible for Venera was working under enormous pressure to finally succeed. The decision was made to redesign the lander completely, with the explicit assumption that the surface conditions were as bad as the worst predictions, and possibly worse. The new lander would have to be built with this assumption baked into every component. That was Venera 7. Venera 7 launched on August 17, 1970. It was redesigned from the ground up. The pressure vessel was titanium, capable of theoretically withstanding pressures up to 180 atmospheres, well beyond what was expected at the surface. The thermal insulation was layered. The internal components were packed with lithium nitrate trihydrate, a salt that absorbs huge amounts of heat as it melts, designed to keep the electronics cool for as long as possible after landing. The whole package was built to a single goal: survive on the surface long enough to send something back. It arrived at Venus on December 15, 1970. The descent did not go as planned. The parachute partially failed. The spacecraft fell faster than it should have, hitting the surface at about 17 meters per second. It bounced. It came to rest on its side, with the antenna pointed mostly away from Earth. The signal was weak, much weaker than expected. For about a half-second after landing, the engineers in the control room thought the mission had failed. The data did not seem to be coming through. They assumed the lander had been destroyed. Then someone, days later, going back through the recordings, noticed that there was a faint, intermittent signal in the data. 23 minutes of weak telemetry. The lander had survived. It had been transmitting all along. Just very, very faintly. 23 minutes of static. That was the first message anyone had ever received from the surface of another planet, and it was nothing more than a thin trickle of data, almost lost in the noise. But it was real. The signal carried temperature readings, pressure readings, confirmation that the surface of Venus was, in fact, 475 degrees and 92 atmospheres, exactly as the previous probes had predicted on their way down. Venera 7 was the first human-built object to land on another planet and survive long enough to transmit data from the surface. And it lived for 23 minutes. Then Venus killed it. That set the pattern. Every Venera mission that followed would push the survival time forward by minutes, by tens of minutes, by improvements in design and materials. But every one of them would die on the surface, eventually, in the same way. The heat would seep through the insulation. The lithium nitrate would melt and absorb everything it could absorb, and then it would be saturated. The electronics would warm. The components would fail. The signal would degrade and stop. The probe would sit on the surface, in the dim red-orange glow, slowly cooking, while 100 million kilometers away, the engineers watched the line on the screen go flat. Then they would build the next one, and try to push the time a little further. The next breakthrough came in 1975, with Venera 9 and Venera 10. These were the first probes designed to do something Venera 7 and 8 had not been able to do. They were designed to take a picture. Venera 9 launched on June 8, 1975. Its companion, Venera 10, launched 6 days later, on June 14. Both were larger and more sophisticated than their predecessors. Both included cameras. Both were aimed at landing, surviving, and sending back the first images ever taken from the surface of another planet. Venera 9 arrived at Venus on October 22, 1975. It descended through the atmosphere on parachutes, slowed by the increasing density of the air, and finally settled on the surface near a region called Beta Regio. The lander deployed. The camera lens cap blew off as planned, and the spacecraft began transmitting. For 53 minutes, Venera 9 sent data back to Earth. In that time, it returned the first photograph ever taken from a surface of Venus, and the first photograph from the surface of any planet other than Earth and the Moon. The image was a black and white panoramic shot. It showed a flat plain, scattered with sharp-edged rocks of various sizes. The rocks were younger than expected, with edges that had not been worn down by erosion. The light was dim but clearer than the engineers had expected. The visibility was good enough to see the horizon. There was, contrary to some early speculation, no thick obscuring fog at the surface. Venus was hot and dense and crushing, but it was visually clear. You could see across it. Then the lander died. 3 days later, Venera 10 landed about 2,000 kilometers away, in another region. It also returned a photograph, again black and white, again showing a rocky plain. Different scenery. Same overall character. Sharp basalt slabs. Dim ambient light. No fog. A horizon. The two photographs together gave humanity the first real glimpse of what the surface of Venus actually looks like. Venera 10 lasted 65 minutes. Picture, for a moment, what the engineers in the Soviet Space Agency saw on those days. A small lander, sitting on the surface of a planet that nobody had ever directly observed. A camera that, against everything the engineering predicted, had survived long enough to capture an image. The image arriving line by line, on a slow telemetry feed, the way images arrived from spacecraft in the 1970s. Each new line of pixels showing more of a place no human had ever seen. And then, somewhere around the 53rd minute, the signal degrading, the image not quite finishing. The lander's electronics losing functionality, one component at a time, as the heat penetrated the insulation and saturated the heat sink. The last lines of the image arriving fragmented, then the signal stopping. Venera 9 had given humanity its first photograph from the surface of Venus, and then it had died, and there was nothing the engineers could do but watch the data trail end. These two missions changed something. Before Venera 9 and 10, the surface of Venus had been a theoretical place. Numbers on charts. Predicted atmospheres. After them, the surface of Venus was an image. A real photograph, taken by a machine that had stood there briefly, that had transmitted what its camera saw, that had then been killed by the planet. We have seen the surface. We have not been there. That is the strange truth about Venus that the Venera 9 and 10 photographs introduced. We had become eyewitnesses, in a sense, through the cameras of dead machines. We knew what the place looked like. We had seen the rocks. We had seen the dim red-orange light filtering down through the clouds. We had a real, photographic record of the surface of our nearest planetary neighbor. But we had not been there. Not in the way being somewhere usually means. No human being had ever stood on those rocks, or felt the pressure, or seen that horizon with their own eyes. No human being ever would. The machines had given us an image. The machines could not give us experience. The next missions tried to deepen the picture. Venera 11 and Venera 12, launched in 1978, both returned data from the surface, but neither one returned successful images. The lens caps on both probes failed to release. Venera 11 transmitted for 95 minutes. Venera 12 transmitted for 110 minutes. The numbers crept upward, mission by mission, as the Soviet engineers refined their designs, but the cameras stayed dark. Then, on March 1, 1982, Venera 13 landed in a region called Phoebe Regio, and Venera 13 was different. Venera 13 was the most successful surface mission to Venus in the history of spaceflight. It still holds that record today, more than 4 decades after it landed. The probe touched down at 3:57 Universal Time Coordinated on March 1, 1982, on a basaltic plain east of Phoebe Regio. The descent had taken about an hour, with the lander breaking through the upper atmosphere, deploying parachutes through the cloud layer, and then descending the rest of the way using only atmospheric drag and a damping ring. By the time it reached the surface, it was moving at about 7.5 meters per second, and it touched down softly enough to remain operational. For the first time in any Venera mission, the lens caps on both cameras released cleanly. The cameras began taking pictures. The lander began transmitting. Venera 13 was equipped with color cameras, not just black and white, like Venera 9 and 10, but full color. The first color photographs of the surface of another planet were taken in the next few minutes. The images came back slowly, line by line, as the data was relayed to the orbiting flyby spacecraft, and then back to Earth. They showed a strange, beautiful surface, flat platy rocks of orange-brown basalt, scattered across a plain that extended to the horizon. The sky above was a yellowish color, dimly lit by sunlight filtering through the cloud layers. Parts of the lander itself were visible at the bottom of each frame, including the semicircular lens cap that had fallen onto the rocks beside the spacecraft. There were even tones in the image, different shades of orange and yellow, the texture of the rocks, the way the light caught their edges. These were color photographs from the surface of Venus, taken by a machine that knew it was probably going to die in less than half an hour. It did not die in half an hour. Venera 13 had been designed for a planned operating life of 32 minutes on the surface. That was what the engineers thought their thermal protection could maintain. After 32 minutes, the lithium nitrate would have absorbed all the heat it could absorb, and the internal temperatures would start climbing past the limits of the electronics. After 32 minutes, by every reasonable estimate, Venera 13 should have stopped working. It did not stop working at 32 minutes. It kept transmitting. 40 minutes, 50, 60. The engineers watching the data could see the internal temperatures climbing. They could see the systems beginning to fail one by one. The drilling arm, which had successfully sampled the surface and analyzed it as basalt, similar in composition to Earth's oceanic basalts, had stopped responding around the 45-minute mark. Some of the meteorological sensors had drifted out of calibration. The cameras kept producing images, though. 90 minutes. 100. The lander was now operating well past any expected duration. Every minute past 32 was uncharted territory. The Soviet engineers, who had designed the lander to die at half an hour, were now watching it survive at 3 times that duration. 127 minutes after touchdown, the signal finally faded. Venera 13 had operated on the surface of Venus for 2 hours and 7 minutes. It had transmitted color photographs. It had recorded soil composition. It had measured atmospheric properties. It had even, for the first time in any planetary mission, recorded sound. A microphone on the lander had captured the noises of Venus itself. The wind, the lens caps falling, the action of the drilling apparatus, the sounds of the lander hitting the regolith. These were the first sounds ever recorded from another planet. 2 hours and 7 minutes was, and remains, the longest anything human-built has ever lived on the surface of Venus. Stop and think about that number for a moment. In 2 hours and 7 minutes, you could watch a feature-length film and not quite be done. You could drive from one city to another. You could have a long conversation with a friend over coffee. By human timescales, 2 hours is not a long time at all. It is an evening. It is a movie. It is a brief stretch of an ordinary day. That number, 127 minutes, is the upper limit of human technological survival on the Venusian surface, set in March of 1982 by a Soviet engineering team using titanium pressure vessels and chemical heat sinks. In the 4 decades since, no probe has surpassed it. No mission has even attempted to. The Venera 13 record stands. There is something almost poetic about that fact. The Soviet space program ended. The Soviet Union itself ended. Less than a decade after Venera 13 landed, the technology of the early 1980s was eventually surpassed in nearly every other domain of spaceflight. We have built better cameras, better computers, better propulsion systems, better materials in the years since, but we have not built anything that has lived longer on Venus. Venera 14, the twin lander, arrived 4 days after Venera 13, on March 5, 1982. It landed about 950 kilometers southwest of Venera 13, near the eastern flank of Phoebe Regio. It also took color photographs. It also returned soil samples. It survived for 57 minutes before its systems failed. The Venera program would go on to launch Venera 15 and 16 in 1983 as orbiters, and then the Vega 1 and Vega 2 probes in 1984, which deployed both balloons into the upper atmosphere and landers to the surface. The Vega landers each survived less than an hour. After that, the program ended. The last Soviet lander to operate on the surface of Venus did so in 1985. In total, 10 landers reached the surface and returned data. Their survival times, in chronological order, were 23 minutes, Venera 7, 50 minutes, Venera 8, 53 minutes, Venera 9, 65 minutes, Venera 10, 95 minutes, Venera 11, 110 minutes, Venera 12, 127 minutes, Venera 13, 57 minutes, Venera 14, and roughly 56 minutes each for Vega 1 and Vega 2. The pattern is clear. The best engineering of the most ambitious planetary surface program of the 20th century, using the hardest materials and the most aggressive thermal designs available, was able to keep machines alive on Venus for, at maximum, 2 hours and 7 minutes. A human being is not a machine. A human being is not made of titanium. A human being does not have a lithium nitrate heat sink built into its torso. A human being is a fragile water-based system, evolved for 1 bar of pressure, 15 degrees Celsius, and an atmosphere that contains oxygen. If the longest a hardened titanium pressure vessel ever survived on Venus is 127 minutes, the question of how long a human being would survive becomes very simple. The answer is the title of this video. Now we have to look in detail at why. Imagine, for a moment, the scenario the title of this video describes. A human being, in a spacesuit, has descended to the surface of Venus. Their lander has touched down on a basaltic plain. Inside the suit, the conditions are kept at Earth-like norms. 1 bar of pressure, 20% oxygen, around 15 to 20 degrees Celsius. The suit is the only thing between this person and the planet around them. The suit fails. Maybe a seal ruptures. Maybe a connector cracks under thermal stress. Maybe the visor of the helmet breaks. The exact mechanism does not matter. What matters is that, in this scenario, the boundary between the inside of the suit and the outside of the suit is suddenly gone. What happens in the first second? Here is the honest answer. In the first second, every fatal process begins. None of them complete, but all of them start. And once they have started, they cannot be reversed. Let us walk through them, one by one, in the order of their effects. The first thing that happens is pressure equalization. Inside the suit, the pressure is 1 bar. Outside the suit, the pressure is 92 bars. The moment the suit fails, the surrounding atmosphere rushes in to equalize. This is not a gentle process. This is a sudden inrush of dense, hot, carbon dioxide-rich air, at 92 times normal atmospheric pressure, into a body and a space designed for one. To put this pressure in human-relatable terms, imagine the deepest free dive any human has ever performed. The world record for unassisted free diving is around 130 meters underwater. At that depth, the pressure is about 14 bar. Divers who attempt this depth must train for years, must ascend slowly, must equalize their ear pressure constantly during the descent, and even with all that preparation, they often suffer lung squeeze, sinus injury, and other pressure-related trauma. The pressure on the surface of Venus is more than 6 times what those world-class divers experience at maximum depth, and it arrives instantly, with no descent time, no preparation, and no equalization possible. The first effect of this is on the lungs. The lungs are full of air at 1 bar. The atmosphere outside is now 92 bar. The pressure differential, in a fraction of a second, compresses the lungs from the outside. Air is forced out of the airways. The chest cavity is pushed inward by the dense atmosphere. The mechanical structure of breathing, the system of muscles and ribs and diaphragm that lets a human take in air, suddenly has to function against 92 times the resistance it was built for. It cannot. The lungs do not breathe at 92 bar. They cannot expand. They cannot draw in air, because there's no room to expand against the pressure outside. Whatever air is inside them is compressed, mostly out, mostly down toward the throat. The lungs collapse. This happens in roughly the same kind of time frame that a deep-sea diver experiences chest collapse if they descend too quickly without protective equipment. On Venus, the descent is instantaneous. The pressure does not rise gradually. It is already there, in every direction, as soon as the suit fails. The lungs collapse essentially at the moment of contact. That is the first system to fail. The second is the breathing reflex itself. The body, in a moment of stress, will try to inhale. The autonomic nervous system commands a breath, but the breath is impossible. There is no oxygen in the surrounding air. The atmosphere is 96% carbon dioxide. Even if the lungs could draw it in, even if the chest could expand against the pressure, the air going in would not contain anything the body can use. There is no oxygen exchange possible. The body cannot extract oxygen from carbon dioxide. The breath, if it happened at all, would not refresh the blood, and the air going in would not be cool. It would be 467 degrees Celsius. Atmospheric carbon dioxide at the surface temperature of Venus, hot enough to begin damaging the soft tissues of the airway, the inside of the mouth, the lining of the throat, in the same instant it arrives. Consider, for a moment, the temperature of household ovens. A standard kitchen oven, set to its highest baking temperature, reaches around 250 degrees Celsius. Self-cleaning ovens, in their cleaning cycle, reach around 470 degrees. The air inside Venus's atmosphere at the surface is hotter than a self-cleaning oven at maximum temperature, hotter than any environment that any human-related material would normally experience. Inhaling that air, even if it were possible, even if there were oxygen in it, would itself be lethal. The mucous membranes of the airway are made of soft tissue. Soft tissue does not survive contact with air at 467 degrees, even briefly. The damage would be immediate, and it would be severe. The third effect is on the body's thermal system. Human skin and tissues begin to suffer thermal injury at temperatures well below boiling, at 467 degrees, in an atmosphere 92 times denser than air on Earth. The heat transfer from a surrounding environment to the body is enormous. Dense gas conducts heat much more efficiently than thin gas. The thermal energy flowing into the body in the first second is far higher than the body could ever dissipate. But here is the important detail. The body does not vanish. The body does not catch fire. The body fails system by system. Breathing fails first. Heat injury begins immediately. Pressure compresses every air-filled space. Consciousness would not survive long enough to understand the surface. This is the part of the story where it becomes important to be honest and to be clinical, and not to sensationalize. The forensic truth of what happens to a human being on the surface of Venus is severe enough on its own. It does not need exaggeration. The lungs collapse from external pressure. Oxygen exchange ceases. The body cannot breathe. The skin and exposed tissues begin to suffer thermal damage from the surrounding heat. Consciousness, deprived of oxygen and overwhelmed by pressure trauma, ends within seconds. There is no second two in which a human being can take action. There is no second two in which a person reaches back toward the lander. There is no second two of awareness that this is happening. The first second is the entire story. What happens after the first second is, in some ways, a continuation of what already started. The body has lost consciousness. The lungs have collapsed. The breathing reflex has been overridden. But the body, as a physical object, continues to undergo changes for some time after death. Here is the broad outline of what happens, second by second, after consciousness ends. In seconds 2 through 5, the body's core temperature begins to rise. The dense hot atmosphere is delivering thermal energy to the body at a rate the body cannot match. The skin reaches the temperature of the surrounding air faster than would happen in thinner atmospheres at the same temperature. But here is an important detail. At 92 bars of pressure, the boiling point of water rises significantly. Water under that much pressure does not turn to steam at 100 degrees, so the water inside the body does not flash to steam the way it would in vacuum. It stays liquid, and it heats. The body does not explode, or shatter, or do any of the dramatic things that some people imagine when they hear about pressure differences. Water and tissue under high pressure stay together. The body becomes a record of the pressure. In seconds 5 through 10, the thermal load continues. The internal organs, insulated by layers of tissue, take longer to heat than the surface. The brain, deprived of oxygen, has already lost most of its function. Within seconds, the body has stopped functioning as a living system. This is what failure system by system looks like, in real time. Not instant disintegration, sequential collapse. Each system in the body fails because it cannot continue to function in the conditions of Venus, and each system fails on its own timescale. It is a clinical, forensic process. It is not the sensational horror that people sometimes imagine. It is the body of a human being, designed for one set of conditions, finding itself in another, and ending in the way that ending must happen. There is no recovery from this point. There is no medical intervention that could be performed, even if it were instantaneous. Each individual injury, in isolation, might be survivable in a hospital. All 3 injuries arriving at the same moment, in an environment where rescue is physically impossible, leaves no path back. The body fails. Then the body remains. And what the body becomes, after it has stopped being a body, is the question we turn to next. After consciousness ends, the surface continues acting on the body as a physical object. Heat, pressure, and dry carbon dioxide keep altering what remains. The details of that long, slow process are less important than the conclusion. Venus does not preserve its visitors. In the first hour, the body's core temperature reaches the temperature of the surrounding atmosphere. The cellular structures break down. Proteins denature, the same way they do in any extremely hot environment. But there is no oxygen on Venus, so the body undergoes thermal breakdown without combustion. It cooks without flame. Over hours and days, the body slowly desiccates. Venus's atmosphere is essentially water-free at the surface, while the human body is about 60% water. There is a strong gradient, and water moves from the body into the atmosphere over time. What remains, after days or weeks, is a desiccated form. Not the person, not in any meaningful sense. A small physical record, sitting on the basaltic plains where the body fell. Over the years that follow, the slow surface winds, moving at less than half a meter per second, eventually disturb even that. The remains erode, scatter, and over geological time fade entirely. This is what makes Venus different from any other planet. On the Moon, on Mars, in deep space, a body left behind tends to remain intact for thousands of years, frozen and undisturbed. Venus is the only place where the conditions actively continue to act on a body, mechanically and thermally, after death. A planet that does not preserve its visitors. A planet that absorbs them, in the way only a planet of this kind could. The killing begins immediately. The dying takes longer. But the answer to the title, the answer to the simple question of whether a human being could ever stand on the surface of Venus and survive, is the answer the Venera probes have been giving us, in titanium and lithium nitrate, since 1970. The answer is no. The natural follow-up question, after walking through what would happen to an unprotected human, is whether a suit could change the answer. A spacesuit, after all, is the entire reason any human being has ever survived in the vacuum of space. Astronauts on the Moon walked on a surface where the temperature swings from positive 120 degrees Celsius in sunlight to negative 130 in shadow. They survived because their suits handled it. The spacesuits used on the International Space Station handle hours of vacuum exposure, temperature extremes, and micrometeoroid impacts. The suit is the technology that makes human spaceflight possible at all. So the question is fair. Could a suit, properly designed, allow a human being to step onto the surface of Venus and survive long enough to do something there? The honest answer is this. No suit we currently build for human spaceflight is designed for these conditions. Whether one ever could be built remains an open engineering question. I want to be careful with this answer because the temptation, when describing how hostile Venus is to say flatly that no suit will ever be possible. That is not a scientifically defensible position. It is possible that some future material science, some breakthrough in heat exchange, some new approach to pressurized exoskeletons, could in principle create a vessel that allows a human to walk on Venus. We do not know with certainty that such a thing is impossible. What we can say is that nothing close to such a suit currently exists, and that the engineering challenges, with our present technology, are enormous in ways that the engineering challenges of Mars or the Moon are not. Here is what a Venus surface suit would need to do. It would need to maintain an internal pressure of 1 bar against an external pressure of 92 bar. That is a pressure difference of 91 bars across the suit material, in every direction, at every moment. By comparison, a deep-sea diving suit handles maybe 10 or 20 bar of pressure difference. A nuclear submarine hull handles around 50 bar at maximum operating depth. A Venus surface suit would need to handle nearly twice the pressure differential of a working submarine, while remaining flexible enough for a human inside to move. There is no current material that can do this in a flexible form. Submarine hulls are rigid steel. Diving suits at extreme depths are essentially metal exoskeletons. The suit you imagine, the soft fabric astronaut suit, with a clear visor, cannot exist at 91 bar pressure differential. The shape would collapse. The seals would fail. The visor would crack. A Venus surface suit would have to be more like a small rigid pressure vessel, a kind of one-person submarine, with limbs that bend through complex articulated joints. It would also need to dissipate heat, constantly, aggressively. The body inside, generating about 100 watts of thermal energy through ordinary metabolism, plus the heat being conducted through the suit from the 467-degree atmosphere outside, would need to be exhausted somehow. The standard approach in current spacesuits is a water sublimator, which uses the vacuum of space to evaporate water and carry away heat. Venus has no vacuum. There is no place to dump the heat. A Venus suit would need an active refrigeration system that ran continuously, using stored energy or chemical reactions to push heat out of the suit and into the surrounding atmosphere, against a temperature gradient of more than 400 degrees. There is no current refrigeration technology, in a portable form, that can do this for any meaningful duration. The Venera probes, with their lithium nitrate heat sinks, lasted hours at most before saturating. A human being would need a system that ran for hours or days, not minutes. It would need to be chemically resistant. Sulfuric acid is a serious concern in the cloud layer above the surface, and even at ground level the carbon dioxide atmosphere is corrosive over time at high temperature. Standard spacesuit materials, including the multilayer Kevlar and polymer fabrics used in current suits, would degrade rapidly in this environment. Specialized materials, possibly metallic or ceramic, would be required throughout. It would need to provide breathable atmosphere. This is actually the easiest of the challenges. Compressed oxygen mixed with nitrogen, in standard spaceflight ratios, can be delivered to the helmet through a regulated supply, the same way it is delivered in any pressurized suit. The atmosphere problem is solvable. The pressure and heat problems are not, with current technology. There's no fabric that holds. There's no current spacesuit, anywhere in the world, designed for 92 bar carbon dioxide at 467 degrees. There's no working prototype. There's no published design that has passed engineering review for surface operations on Venus. The closest existing references are submarine hull engineering and high-temperature industrial process equipment, neither of which is designed to be worn by a human and walked around in. If you want to know how seriously the engineering community has taken the challenge of building a Venus surface suit, the answer is mostly not at all. The space agencies that plan future Venus missions, NASA and ESA primarily, are not working on surface suits. They are working on robotic landers, high-altitude balloons, and atmospheric probes. Nobody is building the kind of vessel that would let a human stand on the surface, because the engineering problem, with our current materials and technologies, has no clear solution. That does not mean it is impossible forever. It means that any such suit, if it ever exists, will require breakthroughs in materials science, refrigeration technology, and pressure vessel design that have not happened yet. It will not be a tweak of a current spacesuit. It will be a fundamentally different kind of machine. For now, and for the foreseeable future, the answer to the question of whether a suit could save a human on the surface of Venus is the answer the engineering tells us. Not yet. Not with anything we have. Not with anything currently in development. A human being on the surface of Venus, today, would die in the first second, suit or no suit, because no suit currently exists that would survive longer than the human inside it. Even ignoring humans, the surface of Venus is a place where machines fail. We have already walked through the Venera probes. 2 hours and 7 minutes was the absolute maximum survival time, achieved by the most advanced lander the program ever built. After that, the same heat that kills humans, the same pressure that crushes machines, the same corrosive environment that degrades materials, took the lander apart from the inside. It is worth understanding, briefly, why machines die on Venus, because the reasons illuminate why humans cannot expect to do better. The primary mechanism of failure is heat. Electronic components, the kind that handle data processing, communications, and instrument control on any spacecraft, have temperature limits. Standard silicon-based electronics fail above about 125 degrees Celsius. Specialized high-temperature electronics, using silicon carbide or other materials, can operate at higher temperatures, up to perhaps 300 degrees, but with reduced performance and shorter lifetimes. The surface of Venus is at 467 degrees. No standard electronics can operate at that temperature, even briefly. The Venera approach, and the approach of most surface missions, is to insulate the electronics inside a pressure vessel that includes a thermal sink, usually a salt that absorbs large amounts of heat as it melts. The thermal sink keeps the interior of the lander cool for as long as possible. When the heat sink saturates, the interior temperature climbs, and the electronics fail. The duration of the heat sink determines the survival time. Venera 13's lithium nitrate heat sink was the most advanced version the program built. It kept the interior below operational temperatures for 127 minutes. After that, it could not absorb any more heat, and the lander died. Increasing this duration is hard. Adding more heat sink mass adds weight to the lander, which makes the descent harder, which limits the size of the science payload. There are diminishing returns. At some point, the lander becomes mostly heat sink with minimal instruments, and the scientific value drops below the engineering cost. A second mechanism of failure is pressure. Even with a pressure vessel rated for 92 bar, the seals around any moving part, any antenna mount, any sample collection arm, are stress points. Over time, the high pressure works against any imperfection in the seal. Fluids and gases can leak in or out. Mechanical components can warp. A third mechanism is chemistry. The atmosphere of Venus, while not as aggressive at the surface as the sulfuric acid clouds above, still contains significant amounts of corrosive species. Sulfur dioxide, carbonyl sulfide, hydrochloric acid traces. Over time, these compounds attack metal surfaces, electronics, and any exposed material on the lander. The Venera probes were built with the most chemically inert exterior materials available at the time, but even those had limits. Finally, there's the simple problem of communication. Any lander on Venus needs to communicate with Earth, and the dense ionized upper atmosphere of Venus complicates radio transmission. The Venera missions used a relay strategy, with the descent module transmitting to a flyby spacecraft overhead, which then relayed the data to Earth. This worked, but it limited the time window during which the lander could communicate. Once the flyby spacecraft moved out of range, even a still-functioning lander would have nowhere to send its data. All these limits combine. The result is that Venus is not just hostile to human bodies. It is hostile to the kinds of machines we know how to build. We have been to Venus. We have landed there. We have taken photographs and recorded sound, but we have never been able to maintain a presence there for more than a few hours in the most successful mission ever, and most missions have lasted less than half that. For comparison, the Curiosity rover on Mars has been operating since 2012. The Voyager probes in interstellar space have been operating since 1977. The longest duration spacecraft missions in history measure their lifespans in decades. The longest duration Venus surface mission measured its lifespan in hours. There's a reason for that gap. Venus is, by some practical measure, the worst place in our solar system to put a long-duration mission. Worse than the Moon. Worse than Mars. Worse, in some ways, than the radiation environment near Jupiter or Saturn. The combination of pressure, heat, and atmospheric chemistry is uniquely punishing. If the most ambitious Soviet engineering of the 1980s could only buy 2 hours and 7 minutes of operational time, the prospects for any human-rated mission, with the additional safety margins required for human operations, are vanishingly small. Which brings us, finally, to the most counterintuitive idea about Venus, and the one that turns the whole picture upside down. The surface kills you. But not all of Venus is the surface. Above the deadly surface of Venus, somewhere between 48 and 60 kilometers up, there is a region of the atmosphere that is, by some measures, the most Earth-like environment in the solar system outside of Earth itself. At those altitudes, in the upper cloud layer, the temperature drops from the 467 degrees of the surface down to roughly Earth surface temperatures, 20 to 50 degrees Celsius, depending on the exact altitude. Comfortable, in places, by human standards. The pressure also drops. From 92 bar at the surface, the pressure at 50 kilometers altitude is roughly 1 bar, the same as standing on the surface of Earth at sea level. A human being at that altitude would feel no pressure differential against their body at all. The atmosphere, at that altitude, is still mostly carbon dioxide. There is no breathable air. There are sulfuric acid droplets in the cloud layer that would damage exposed skin. But the pressure and temperature, two of the three things that make the surface immediately lethal, are roughly Earth-like at this altitude. This realization that a layer of Venus's atmosphere has Earth-like pressure and temperature has produced one of the more imaginative ideas in space exploration. The idea is called HAVOC, the High-Altitude Venus Operational Concept. It was developed at NASA's Langley Research Center as a study of how human exploration of Venus could potentially work, given the constraints we have just walked through. The Havoc idea is this. Instead of trying to land humans on the surface of Venus, where they cannot survive, you fly humans through Venus's atmosphere at the altitude where the conditions are mildest. You do this in airships, large helium-filled or breathable air-filled vessels that float at 50 kilometers altitude in the dense Venusian atmosphere. A breathable air mixture, the kind humans breathe on Earth, is lighter than the carbon dioxide atmosphere of Venus. So a large vessel filled with Earth-like air, in the carbon dioxide of Venus, behaves like a hot air balloon in Earth's atmosphere. It floats. It can be steered with simple aerodynamic surfaces. It does not require active lift the way a helicopter does. It just hangs there, in the upper atmosphere, supported by the difference in density between its interior and the surrounding Venusian air. Inside such a vessel, a human being could, in principle, walk around in shirt sleeves. The pressure inside would be the same as the pressure outside, which is the same as Earth at sea level. The temperature could be controlled with modest air conditioning, the same way any aircraft handles temperature. The atmosphere inside would be normal breathable air. The crew would essentially be flying through Venus's upper atmosphere in a small mobile habitat, doing science, observing the planet, and surviving in conditions much more comfortable than what astronauts on the International Space Station experience. Outside the vessel, of course, there would still be sulfuric acid droplets. The materials of the airship would have to be acid-resistant. Any external operations, like deploying instruments or manipulating samples, would have to be done by remotely operated arms, working through chemically resistant hatches. But on the inside, the conditions could be made comparable to a comfortable office building. Imagine, for a moment, the view from inside such a vessel. You are floating at 50 kilometers altitude in the upper cloud layer of Venus. Around you, in every direction, the air is a pale yellow. Sunlight, filtered through the higher cloud decks above, comes down at an oblique angle. The clouds you are inside drift past at speeds that, at this altitude, can reach hundreds of kilometers per hour. The vessel does not feel that motion, because the vessel is moving with the air, the way a balloon on Earth moves with the wind without feeling it. Below you, somewhere through the haze, is the surface. 48 kilometers down, the basaltic plains, the volcanic highlands, the 467-degree atmosphere, the 92 bar pressure, the deadly conditions we have spent this entire video describing. They are still there. They have not changed. They are just below you. Above you, somewhere above the clouds, is space. 60 more kilometers up, the atmosphere thins enough that you would see the stars, the dim shape of Earth in the distance, the sun no different from how it looks from anywhere else in the inner solar system. You are between two extremes, the hostile surface below, the empty vacuum above, and a thin band of habitable conditions exactly where you are. This is not science fiction. This is the actual physics of Venus's atmosphere, and the actual engineering principle behind the Havoc concept. The middle layer of Venus's atmosphere, between 48 and 65 kilometers altitude, is closer to Earth's surface conditions, in pressure and temperature, than anywhere else we could send humans in our solar system today. This is the strange dual nature of Venus. The surface is the deadliest environment a human being could ever encounter. 50 kilometers above that surface, the same atmosphere that kills you on the ground becomes a place where you could, with the right vehicle, live indefinitely. Heaven and hell, stacked vertically. Havoc is not an active mission. It is a concept study. NASA has not committed to building it, and there are no current plans to send humans to Venus's atmosphere on this kind of vehicle. But the concept is engineering grounded. The numbers work. The basic idea of using the dense Venusian atmosphere as a buoyancy medium for a habitable vessel is sound. If humanity ever goes to Venus, in any meaningful long-term presence, the most likely first form of that presence is not on the surface. It is in the air, above the surface, drifting through the upper cloud layer in a mobile habitat that uses the planet's own atmosphere to stay aloft. There's a strange poetry in this. The same atmosphere that crushes the surface, that traps the heat, that turns Venus into the planet we have been describing for the past hour, is also the atmosphere that, at the right altitude, could support human life better than the surface of Mars. The atmosphere is the killer. The atmosphere is the savior. Both at once, just at different altitudes. And once you understand that, you understand why scientists keep being drawn back to Venus, even though the surface is unreachable. There is something there. There is a path forward, if humanity ever wants to take it. It just does not begin on the ground. To close out the science, we have to ask the question that has been hanging over every part of this video. How did this happen? Venus and Earth started in roughly the same place, 4.5 billion years ago. Same protoplanetary disk. Same rough composition. Same general distance from the Sun, in cosmic terms. They were, at the beginning, sister worlds. By every reasonable model of how planets form, they should have ended up similar. They did not. Earth became a habitable world with oceans, an atmosphere, and life. Venus became what we have been describing. Why? The answer, as best we currently understand it, has three parts. The first part is the Sun itself. The Sun was dimmer 4.5 billion years ago than it is today. It has been gradually brightening over its lifespan, the way most main sequence stars brighten as they burn through their hydrogen. 4 billion years ago, the Sun was about 30% dimmer than it is now. That extra dimness made the early solar system colder, on average. Both Venus and Earth received less heat than they receive today. For a while, this may have kept Venus cool enough that liquid water could exist on its surface. The evidence is suggestive, but not settled. Some lines of chemistry, specifically the ratio of two different forms of hydrogen in the Venusian atmosphere, point toward a wetter early Venus. Other recent research, published as recently as 2024, has challenged the picture, arguing that Venus may never have had liquid oceans in the same sense Earth has them. The science is still actively debated. Hydrogen has two isotopes that matter here. Ordinary hydrogen, with one proton and no neutrons, and deuterium, also called heavy hydrogen, with one proton and one neutron. Both isotopes can be part of water molecules. Ordinary water has two ordinary hydrogens. Heavy water has one or two deuteriums in place of the ordinary hydrogen. In Earth's oceans, the ratio of deuterium to ordinary hydrogen is a specific number. We measure it. We know what it is. In Venus's atmosphere, the ratio is dramatically different. There is roughly 120 times more deuterium relative to hydrogen than there is on Earth. This is a chemical fingerprint. It tells a specific story. When ultraviolet light from the Sun strikes water vapor in a planet's upper atmosphere, it can break the water molecule apart. The hydrogen atoms, lightest of all elements, can escape into space, leaving the oxygen behind. Deuterium, being twice as heavy as ordinary hydrogen, escapes more slowly. Over very long timescales, hydrogen drifts away faster than deuterium does. Whatever remains becomes proportionally enriched in deuterium. The very high deuterium to hydrogen ratio in Venus's atmosphere is exactly what you would expect if Venus had once had a large amount of water, which then evaporated into the upper atmosphere, where ultraviolet light slowly stripped away the hydrogen over billions of years. The deuterium stayed. The ordinary hydrogen left. The ratio shifted. Venus might have had a more Earth-like beginning. The evidence is suggestive, but not settled. How much water did Venus have, if it had any? Estimates vary widely. Some models, based on the deuterium evidence, suggest Venus could have had oceans comparable to Earth's, possibly several hundred meters deep across the planet, in its earliest era. Other recent models question whether liquid oceans were ever stable on Venus at all, arguing that the planet may have remained too hot for surface water from very early on. The honest position is that we are still working out which picture is correct. The second part of the answer is that as the Sun brightened, Venus was closer to it than Earth was. Venus is at about 72% of Earth's distance from the Sun. It receives about 91% more solar energy per square meter than Earth does. As the Sun warmed, Venus warmed faster than Earth. Whatever water existed on or near the surface, in whatever form, would have been pushed into the upper atmosphere over time, where ultraviolet light could break it apart. The process we just described. And here is the third part of the answer. The disappearing water did something to the rest of Venus's atmosphere. Water vapor itself is a powerful greenhouse gas. As more water evaporated, more heat was trapped, which evaporated more water, which trapped more heat. A feedback loop. This is the runaway part of the runaway greenhouse. Once it started, it could not stop. Each step made the next step more likely. Whatever water Venus had, in whatever form, was eventually lost. The atmosphere thickened. The temperature rose. The processes that on Earth keep the climate stable, oceans absorbing carbon dioxide, weather cycles distributing heat, plate tectonics cycling material between surface and interior, did not function the same way on Venus. What remained was carbon dioxide, released from the rocks over billions of years through volcanic activity, and not removed from the atmosphere because the carbon cycle that operates on Earth was either never present on Venus or had broken down long before. Earth has carbon dioxide too. Lots of it, in fact. But most of Earth's carbon is locked up in rocks, in oceans, in the long, slow cycle that moves carbon between atmosphere, water, and stone. On Venus, with no oceans, that cycle was broken. The carbon dioxide accumulated. The atmosphere became what it is. The point at which Venus crossed from a cool, wet world into the runaway greenhouse is unclear. Some models suggest it was as recent as 1 billion years ago. Other models put the transition further back, 3 or 4 billion years ago. There's active research on this question, and the answer affects how habitable other planets in the universe might have been at different points in their lives. But the basic outline of the story is roughly understood, even if details are debated. Venus was once a different planet from what it is now, possibly with surface water, possibly with conditions closer to Earth's. Then, somewhere along the way, the climate tipped. The runaway greenhouse took over, and the planet became the place we have been describing for the last hour and a half. Same body, different fate. The reason that line keeps returning throughout this video is that it is one of the central questions about Venus, and one of the central reasons we keep studying it. Earth and Venus started, by every basic measure, as similar planets. One of them ended up with stable surface water and life. The other one ended up as the world we have been describing. Why the divergence happened, when it happened, and whether Venus ever had truly Earth-like conditions, are questions still being actively researched. And the ratio of deuterium to hydrogen in the atmosphere, today, for billion years after the divergence, is the chemical fingerprint that tells us the story. Despite the fact that Venus has killed every machine that ever landed on it, despite the fact that no human will likely ever walk there, the planet has not been forgotten by the space agencies of the world. In fact, the next decade is set to be the most active period of Venus exploration since the Soviet program ended in the 1980s. 3 major missions are currently in development. NASA's Da Vinci mission, scheduled to launch later in this decade, is an atmospheric probe designed to descend through Venus's atmosphere and study its composition in detail. Da Vinci is not a lander in the traditional sense. It is a descent probe designed to take measurements all the way down through the cloud layers, gathering data about the chemistry, the composition, the structure of the atmosphere, until eventually it reaches the surface and stops functioning. The mission is meant to answer some of the most basic questions about how Venus's atmosphere evolved into what it is today. NASA's Veritas mission, also planned for this decade, is an orbiter. It will not land. It will carry radar instruments designed to map the surface of Venus in unprecedented detail, building on the work the Magellan spacecraft did in the 1990s. Veritas will be looking for evidence of recent volcanic activity, mapping the topography, and trying to determine whether Venus has, or once had, plate tectonics in any form. It will give us our best look ever at the surface, even though no one will be on the surface to see it directly. ESA's Envision mission, planned for launch in the early 2030s, is another orbiter, with a different set of instruments designed to study the atmosphere, the surface, and the interaction between them. Envision and Veritas together will give scientists a fuller picture of Venus than has ever existed. Notice the pattern. None of these missions are landers. None of them are designed to put a machine on the surface for any extended period. The space agencies of the world have, in the 4 decades since Venera 13, learned the lesson the Soviet program taught. The surface is too hostile to study from the surface. We will study it from above, from orbit, from descending probes that take their measurements during the fall and accept that the surface is the end of the mission. There is one current concept, called Venus Long Life Surface Explorer, that aims to use high-temperature electronics to build a lander that could survive on the surface for weeks or months rather than hours. The technology, based on silicon carbide rather than silicon, can in principle operate at 467 degrees. But the components for this kind of mission are still in early development. No flight-ready hardware exists yet. If such a mission ever flies, it will be far in the future. The reason this matters is that even a lander that survived for weeks or months on Venus would be a fundamentally different kind of mission than anything we have flown to the surface so far. Imagine, instead of 2 hours of measurements, 2 months. Instead of a few photographs from one location, a slow walking traverse across some piece of the basaltic plains. Instead of a single point in time, a sustained sequence of measurements that could tell us how the surface changes from day to day, if it changes at all. Whether such a mission ever flies depends on whether the engineering challenges can be solved within an acceptable budget, and whether any space agency decides the science would justify the cost. As of today, neither question has a clear answer. For now, the strategy is clear. We will keep looking. From above, the planet will keep its surface mystery. We will accept that and learn what we can, in the ways that the planet allows. We have walked through almost everything Venus has to offer, and almost everything it does to anything that touches it. Before we close out tonight, I want to come back to the title of this video and put a final clear frame around what it means. The title says no human will ever survive a single second on Venus. We have spent the last 2 hours showing why that is true. But single second is not literal disintegration. It does not mean the body vanishes in 1 second. It does not mean the body is destroyed in 1 second. The forensic timeline, as we walk through it, takes longer than that. The lungs collapse essentially at the moment of contact. Consciousness ends within seconds. The full thermal and pressure changes to the body unfold over hours and days. The body remains, in some recognizable form, for a long time after death. What single second means is something more precise. It means there's no first second of human presence on Venus that does not include all the fatal mechanisms operating at full force. There's no version of the experience where a human being arrives, takes a moment to look around, has any awareness of where they are, and then succumbs. The killing happens before any of that can occur. The first second is already the dying. It also means that there is no rescue scenario. There is no airlock to retreat to in time. There is no procedure that an experienced astronaut could perform to extend their life. There's no version of the story where the human, having stepped out, manages to step back. The conditions outside the suit are so completely lethal that any breach of the suit, in any way, in any moment, results in immediate and irreversible damage to the person inside. The killing begins instantly. The dying takes longer. That is the honest version of what the title is saying. The first human to step onto the surface of Venus will not survive a single second of meaningful presence there. They may continue to exist as a body for some time after the suit fails, but they will not be alive in any way that matters, and they will not be coming back. This is true now. It will be true for every future astronaut who ever attempts to land on Venus, until and unless someone builds the kind of pressure vessel and refrigeration system that we have not yet learned how to build. Such a system may never exist. It may exist 100 years from now. We do not know. But until that day, Venus remains what it has been since the moment human beings first measured its surface conditions. The closest planetary neighbor we have, almost the same size as Earth, almost the same gravity as Earth, and the most hostile solid planetary surface any human could realistically try to reach. You can stand on the surface of the Moon, now, with the right suit. You can stand on the surface of Mars, now, with the right suit, if a mission ever takes you there. You cannot stand on the surface of Venus. You will not, in our lifetimes, be able to stand on the surface of Venus. The planet will not allow it. The most Earth-like planet in our solar system is the most hostile place a human will ever encounter. That sentence is the whole story. Everything else we covered tonight, the Venera probes, the Runaway greenhouse, the deuterium ratio, the cloud cities, the second-by-second forensic breakdown, all of it is just the detail beneath that one sentence. The detail matters. The detail is what makes the story scientific rather than merely shocking. But the sentence underneath is the thing. Venus is what Earth could have been. We are alive on this planet because, for reasons we are still working to fully understand, the climate histories of Earth and Venus diverged a long time ago, and ours stayed habitable. That is, in a strange way, the deepest reason to study Venus. Not because we plan to go there, not because we expect to colonize it, not because there is anything human scale to gain from its surface, but because Venus is the closest example we have, anywhere, of what a planet very much like Earth becomes when the things that protect a planet from itself are taken away. It is a warning, in the way only a planet can be a warning. Not a deliberate one, just a present one. Just sitting there, second brightest object in our sky after the moon, beautiful in the evening, lethal up close, tracing the same orbit it has traced for 4.5 billion years, holding its terrible record. And it tells us, in the most direct way any object in the universe could tell us, that the conditions which make a planet habitable are not guaranteed. They are the result of specific histories, specific events, specific climate balances that, once tipped, may not tip back. Earth has those conditions. Earth has them now. Whether Earth will keep them indefinitely is a question Venus does not answer. But Venus reminds us that the question is real. Machines have landed. Humans have not. And the surface explains why. In a moment, I am going to let the night settle. But before I do, I want to leave you with one image to take into the dark with you. When Venus rises in the morning, just before dawn, it is sometimes called the morning star. When it sets in the evening, just after sunset, it is sometimes called the evening star. The same planet, depending on the time of year, can play either role. It is the brightest thing in the sky after the sun and the moon. People have looked at it, named it, written poetry about it, and built temples in honor of it for as long as there have been people on Earth. For most of human history, no one knew what Venus actually was. It was a light, a symbol, a star that walked among the others. The ancient Babylonians tracked it. The Maya tracked it. Greek and Roman astronomers gave it the names of their goddesses of love and beauty. Across thousands of years, almost every culture that watched the sky watched Venus, and almost every culture saw it as something beautiful. For most of those thousands of years, no one had any way of knowing what was actually under the bright cloud cover. It was visible. It was named. It was tracked across the sky with the same careful attention given to all the other wandering lights. But nothing about its actual nature, its temperature, its pressure, its atmosphere, was knowable from the surface of Earth alone. Then, in the 20th century, we started to find out what was actually there. The Mariner missions of the 1960s, the Venera probes of the 1970s and 1980s, the radar maps from Magellan in the 1990s, the slow accumulation of data from a planet that, the closer we looked, became more and more difficult to imagine standing on. The brightest beautiful thing in our sky turned out to hide one of the most hostile solid environments in our neighborhood. And yet, when you go outside tonight, after this video is over, and the sun has set, and you look toward the western horizon, Venus will still be there, pale, brilliant, beautiful, hanging low over the rooftops, the same way it has hung in human skies for as long as there have been humans to see it. It does not look like what it is. It will never look like what it is. From 100 million kilometers away, it is still the loveliest thing in the night. Up close, it would kill you in the first second of contact. That is Venus. That is what we have been describing for the last 2 hours. The brightest planet, the closest thing to Earth we have, the world that started the same as ours, and became the warning of what could have happened to us. There is something almost gentle about ending the video this way, even though the planet itself is not gentle. Because here's what is true. Most of us will never see Venus up close. Most of us will never have to contend with the conditions on its surface, except as a thought experiment. For all but a handful of human beings, Venus will remain what it has always been, a point of light in the sky, a beautiful brightness that appears at sunset or before dawn, a small jewel on the horizon that has been a part of the human visual landscape for as long as we have been looking up. That is, in the end, the version of Venus that matters most for the people watching this video. Not the lethal surface, not the second-by-second forensic breakdown, not the engineering challenges that prevent us from ever standing there. The version that matters is the brightness, the familiar light, the thing you can see for yourself on any clear evening, with no equipment, just by walking outside and looking west. And somewhere in your mind, take with you the image of Venera 13, sitting on a basaltic plain in Phoebe Regio, in March of 1982, taking color photographs of orange-yellow rocks under a yellow sky for 2 hours and 7 minutes before the heat finally killed it. That little titanium pressure vessel was the closest any human-built thing has ever come to standing on Venus. It survived longer than anything before or since. Its photographs are still some of the only pictures we have of the surface. We have seen the surface. We have not been there. We will not be there in our lifetimes. Probably not in the lifetimes of any of our children or our grandchildren. Maybe never. The planet does not want us. The planet, in the indifferent way planets have, simply is what it is. And what it is happens to be the end of any human being who tries to touch it. If the night is clear enough where you are, go look at Venus tonight. Hold what you have learned about it in your mind, and let it sit there alongside the visual beauty of it in the sky. Both are true. The brightness is true. The beauty is true. The lethal surface, 467 degrees and 92 atmospheres, and unbreathable carbon dioxide, is also true. Both at once. Same planet, different aspects. That is, in a way, what astronomy keeps teaching us, that the things in the sky are never quite what they look like from where we stand, that the closer we get, the stranger they become, that the universe is full of objects that wear one face from a distance and another face up close, and that the work of science is mostly the work of holding both faces in mind at the same time. Venus is the most extreme example of that lesson, in our own neighborhood. Beautiful from here, fatal from there. Same planet, same atmosphere, same orbit it has traced for 4.5 billion years, just observed from 2 different distances. Good night. Sleep well wherever you are.